The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to this webinar. My name is Michael Evangelista and I will be your moderator for today. Just a few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want in the question or in the chat box, and those questions will be answered in a Q&A segment. By the way, the recording and certificate of this webinar will be sent out in 2 days' time. And our topic for today is about the distance protection basic. It is a pre-recorded webinar from the USA, and it is presented by Abel Gonzalez. So guys, without any further ado, let's start the webinar. Grace?
Hello everyone, thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is Basics of Distance Protection. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Our presenter today is Abel Gonzalez, Relay Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Abel.
Hey, thanks for the presentation, Michael. Okay, let's get started with the basics of distance protection. On this presentation, we will be introducing the reasons for using distance protection on power systems. We will be talking about how we do the calculation of impedances used in the settings of the distance protection relays and distance protection systems in power systems, and we will be talking a little bit about compensation factors used in distance protection, especially for the ground fault protection. We will be talking about the source impedance ratio, what that means, what influence does it have on the protection of lines using distance protection systems. And we will be then talking about the characteristics of distance protections, the ones used, the most used ones, namely the mode characteristics and the quadrilaterals. And then we will talk a little bit about polarization methods used for the supervision and the calculation of the characteristics of the distance protection, and then we will introduce protection schemes used with distance protection systems. And as an introduction, I want to present the, let's say, physical reasons for why distance protection is used in systems. If you guys remember the equation for the resistance of the conductor, here we have the resistance as a function of the resistivity and the area, and it's directly proportional to the length of the conductor. So we can say that the resistance of the conductor is directly proportional to its length, and we can say that the longer the conductor, the bigger the resistance, the shorter the conductor, the shorter the resistance. With the inductance, in the case of a transmission line, we can devise a similar equation in which the inductance is a factor of the geometry of the system and also the distance along the line. So the longer the line, the longer the inductance. And the reason why that is relevant is because the reactance is directly proportional to the inductance, and we can also get an equation where we say that the reactance is the reactance per unit length of the line times the distance or the length of that line. Then we can put it all together, and we can say that, for instance, in a short line where we can, neglect the effect of the shunt capacitance on the line, we can say that the impedance, which is equal to the resistance plus the reactance, as a complex number, we can come up with a distance times the unit or the per unit length of the per unit impedance of the line, which means that we can say that the impedance of the line is a function of its length. If we include the capacitance in this, the equations are going to be a little bit different, a little bit more complicated, but we can still say that even with the inclusion of the capacitive effect in longer lines, we can still say that the impedance of the line is a function of its length. Actually, one of the reasons why impedance protections were first introduced is because the impedance per unit length of the line is assumed to be constant, and then a measurement of the impedance can tell you where along the line a particular fault can be located. So if we, here is the equivalent circuit that we can use for this short line. And the question here is, does it mean that if I am somehow able to measure the voltage and the current on the line and calculate the impedance, I could tell the length of the line? Not quite. It depends, of course, of the fact that the current circulating on the line at the time of the measurement depends only on the impedance on the line. And when is it that that happens on the system? Well, it happens when you have a fault, because if you have the line and the power that it's circulating through the line, then the impedance, the apparent impedance that you measure on that line is going to be more related to the power circulating through the line than to the impedance of the line. But if you collapse that power, as it happens when you have a fault on the line, then you can say that if you're able to measure the voltages and currents at one point, then you can use the calculation of those resulting calculation from those voltages and currents, which is the impedance, as the measure of the length of the line. So if we can use those voltages and currents, in this case, for instance, we can say that the impedance measured in this point here on the where we see Vs would be Vs minus Vr divided by the current, and that's the impedance of the line. If you have load circulating, then that impedance is related to the load. But if you have the case of a fault in which the voltage at this point collapses, and we can then divide the line in whatever it is, whatever the impedance we have before the point of the fault and the impedance that we have after the point of the fault. So we can call this the impedance of the fault, and then we can say that if we divide the voltage by the current, in this case, then we can have the impedance to the fault, and then we can use some relationships to tell us at what point in the line did the fault happen, right? So then we have things like this, where on one side of the line we have the impedance to the fault, and on the other side of the line we have the complement of that impedance to the fault, which is the total impedance of the line minus the impedance of the fault, because we are essentially dividing this line in two. We can do the same from the other end, which is useful because these lines are protected from not just from one end. So in this case, we know that the impedance to the fault equals the voltage at the source, or the voltage here, divided by the current of the line, right? Which in this case equals the current at the fault. And remember this equation here, so we can tell the distance to the fault by simply calculating the impedance to the fault, and then taking this and determining the distance to the fault by voltage divided by the unit length impedance times the current that's circulating to the line at the time of the fault. So if we have a system that's working in proper conditions, and we have a measurement point here, we can say that the apparent impedance as seen from this point will have a characteristic like this, where it will be very close to the resistive axis of the Rx diagram. In this case, what this means is that, yeah, we have a high power factor, which means that the system is operating properly. You have a lot of power circulating through the line. And at the time of the fault, you have something that changes that behavior. Why does the behavior change? Because when we cut the line in here, because there is a fault, we essentially make this voltage zero, or as close to zero as can be. Then the impedance that's being measured from this point will be only the impedance of the line. And you see that change in impedance from an impedance that was very close to the resistive axis to an impedance that's very close to the reactive axis happens when you have a fault, because lines are essentially reactive in nature. Most of the impedance of the line happens to be inductive. So you have this changing characteristic of the measured or apparent impedance as measured from this point. This is part of the measuring principle that we use for calculating the impedances that are used on impedance relays. Now, the impedance would be simply, if we can take this line and we don't consider any three-phase system, well, it would be simply the voltage measured at this point divided by the current that's circulating through the fault and back to the source. And then we can say that the impedance to the fault is simply this voltage divided by this current. Now, we know that that is not that simple. Why? Well, because these systems are three-phase, and in the case of three-phase systems, we have to take into account the differences between three-phase faults, face-to-face faults, and face-to-ground faults in terms of how the impedances are calculated. For instance, for a three-phase fault, if we say that the fault happens at some point in the line where the three phases are bolted together, so essentially the voltage here is zero. If the system is balanced, then we can consider this point to be the neutral, and since it is a three-phase fault, the current through the neutral is going to be zero, so the impedance to the fault can be calculated as any of the impedances of the phases, and we can say then that the impedance to the fault will be simply the voltage at the measurement point to the neutral divided by the current that's circulating in that particular phase. Now, the impedances that we're using here, that we are calling ZA to the fault and ZB to the fault and ZC to the fault, are the positive sequence impedances of the line to the point of fault. Okay? Now remember, this is a three-phase fault. No unbalance is considered in this case, so we are only considering the positive sequence impedances of the line to the point of fault. Okay? Now, every representation on the Rx diagram will include the locus of the line, which is this one, and it will end at the point where we calculate the impedance to be. The impedance of the whole line would be longer, but the impedance of the to the point of the fault only reaches this point here. In a case of the face-to-face fault, we can now discard whatever is happening on phase C for an A to B fault. And in this case, what we are doing is we're calculating the voltage between these 2 points, okay? And we can notice that for a face-to-face fault, the current that will circulate between A and it will go back through B. So we can say that IA equals minus IB. And then we can say that that current will be equal to the voltage from one phase to the other divided by 2 times the impedance, because we have twice the impedance in this fault loop. So the impedance, in this case, the impedance calculated to the point of the fault will be the voltage divided by twice one of the currents in the phases. The resulting diagram is always the same because in here what we have is the angle of the line, okay? There's no modification to the angle of the line because we're not considering any resistance at the point of the fault. So we are simply saying that the angle that we have here is exactly the angle of the line. In the case of the face to ground fault, it's a little bit trickier, and we're going to spend a little bit more time on this one because of the effect that this type of fault has on the selectivity of these systems, and also because we are going to talk about the compensation methods that are used for this type of fault. Now, in this case, we can say that if it is a face to ground fault, we can introduce the impedance of the neutral loop here, and we can take the voltage to the neutral at this point, at the point of measurement, and we can say that the neutral current 3I0 equals the phase current. If you see, they're in series over here. So that then we have VA equal to I times the positive sequence impedance of the line plus 3 times I0 times the impedance of the neutral. So in this case, we say IA equals 3I0, so we can take a common term here, IA, and then we can calculate the impedance, in this case, as VA divided by IA. But see, notice that in this case, the impedance of the fault, which is what we are trying to determine, is modified. It's modified by a term that is the impedance of the neutral. And it is an impedance that right now we do not know. We don't know what the value of that impedance is. And that's what we are going to try to determine later on. Okay? So what I want you to notice here is that since we have the influence of the neutral, then the characteristic is switched. It is changed. So in this case, we are going to have an influence of this impedance that is not going to allow us to properly determine the impedance of the line, the positive sequence impedance of the line to the point of the fault, because now we have two unknowns here. And what's going to happen is that if we are using, for instance, this type of protection, we are looking for it here, but we're going to see it here. We're going to see a higher impedance, which means that for this particular case, if there is no compensation applied, even though the fault is here and it's clearly on the limit, then the system will not, or the protection will not operate. So we have to find a way to counter the effect of that for the face to ground faults. Now, how do we do that? Well, we are looking for this guy here. We don't know what the value of this guy is. So what we have to do is we have to use the sequence networks. We have to go and decompose this system into the sequence components of that system. So we have to determine who this guy is, and for that we are going to go and use this single line to the point of the fault, and now we are going to use the sequence network equivalent circuit, which in this case, since the voltage of the fault is 0, we are simply connecting in series the three networks, and now here we have the positive sequence networks, the positive sequence network with its positive sequence current and the impedance, and we also have the source, the voltage at the source here, the impedance of the source, or the positive sequence impedance of the source, and then we have the same for the negative sequence network with its own currents and impedances, and for the zero sequence network with its own current and its own impedance. In this case, we have that the three currents are the same. We also know from the line design that the positive sequence impedance and the negative sequence impedance are the same. And we can say that because this is the definition, the Megger definition of sequence component, that IA, which is one of the terms of this equation that we're looking for here, equals the sum of the three sequence components. And in this case, it's 3I0 because I1, I2, and I0, since this is a series circuit, are the same. So we can say that IA equals 3I0 or 3I1 or 3I2. It will be relevant later as we go with the rest of the equations. So now here we can also say that V1, the voltage here, equals the current times the impedance, its own current times its own impedance. So V1 equals the positive sequence current times the positive sequence impedance. And then for V2 and V0, we can use the same equations. And then we can say that since I1 equals IA divided by 3, then we can say that V1 equals IA divided by 3 times the positive sequence impedance. V2, we can have the same equation. And for V0, we can say it's IA divided by 3 times the zero sequence impedance. So now we can put it all together. VA, the same as IA, equals the sum of the three voltages for the three sequence components. Now we have simply by substituting the values of V1, V2, and V0 that we have here on the right-hand side, we can take IA divided by 3 as a common term here, and we have two positive sequence impedances, and we have one zero sequence impedance here. So this equation comes from simply putting these three in here and doing some rearrangement. Now we can divide VA divided by IA, leaving this 1/3 on this side of the equation, and we are going to have 2/3 of this impedance, the positive sequence impedance, plus 1/3 of the zero sequence impedance. Now, VA divided by IA is what we are looking for because we want to know who this guy is, but for that we have to determine VA now. We now know what VA divided by IA is in this network here. And now VA divided by IA is this term, which looks familiar because it's the same, except it's 2/3 of this plus something else. So what we need to do is we need to make this whole in order to take this term out and realize what the term is. So what I do is I simply add 1/3 and subtract 1/3 of this positive sequence impedance, and then I come up with VA divided by IA equals the positive sequence impedance to the fault plus one term here that has to be equal to the impedance on the ground that I'm looking for, on the impedance on the neutral that I was looking for. So this ZLN equals 1/3 of the zero sequence impedance minus the positive sequence impedance is called the ground return or residual impedance. And we are going to use that to calculate the compensation factors as follows. Okay, let me put this all, okay. Now, we know that VA divided by IA, which is this impedance here, is the apparent impedance of the ground loop. So the apparent impedance of the ground loop, set G, is this plus 1/3, because this is what we came up with in the equation before, and we can put this in this form here. Now we want to rearrange this so that we can use this equation because it's in its present form is not very useful. So now we simply do some math again, and we add and subtract and do some magic here. And then we come up with this ZG simply by rearranging this, okay? We rearrange this equation over here, and then we added and subtracted 1, and we came up with this equation over here at the end, which is the positive sequence impedance to the fault times 1 plus this term here. And this term here, those of you who have already done some testing on protection, on distance protection, you will recognize this term as the residual compensation factor, Kn. And now we can use this Kn in this equation, And we can say that VA divided by A equals the positive sequence impedance to the fault times 1 plus this compensation factor. And this allows us to calculate the positive sequence impedance to the fault by simply dividing the voltage and the current and applying this compensation factor. Now, we did some sleight of hand here. We were using the positive sequence impedance to the fault, and then all of a sudden we came up with the zero sequence impedance, the absolute zero sequence impedance, and the absolute positive sequence impedance of the line. This is possible because we can take out the factor that is the fraction of the line that is represented by the fault, because it's going to be the same for the zero sequence impedance and for the positive sequence impedance. We can factor it out. I'm sorry, I didn't put it here. We can factor it out to make it 1, and then now we are talking about the residual compensation factor, which is a factor that is given in terms of the absolute zero sequence and positive sequence impedances of the network. So we have these two compensation factors that I wanted to mention here. This is called the residual compensation factor, Kn, and we also have the zero sequence compensating factor, K0. They are used similarly. The difference is that in one case we have the residual current that we have here, and in the other case we have the zero sequence current. Obtaining the zero sequence current mathematically is very easy. Obtaining the residual current by measurement is also possible. So I guess depending on what do you have available at the point, and also very important, what type of compensation your relay uses, then you will select one compensation factor or another. Now, this is a basics of distance protection webinar. There are many other compensation factors used by relay manufacturers out there. All you have to do is make sure that you're using the proper compensation factors. Otherwise, your tests will be skewed. There are compensation factors like the resistive and reactive. There is also another one that's simply the multiplication of the zeta zero, I mean the zero sequence impedance by the positive sequence impedance, etc. But I'm not going to mention them here. I wanted to bring this here just to mention the fact that you need to compensate when you have single phase to ground faults, and to try and show you how these compensation factors are developed in terms of the equations that you have to use, so that you're not afraid of doing it yourself if in any case you need to. There is a ton of information on about this on the internet, so you can also use that. Now, once we have calculated the impedance, we know the impedance to the fault. What can we use that impedance? Absolutely. And say that if the impedance that I calculated is lower than the impedance to the line, can I trip? Can I use that as a protection criteria? Let's go and talk about, just for a minute, CTs. And why do I talk about CTs? Because remember the equation that we came up for the impedance? The equation always includes the amount of current that's circulating, and the amount of current. How does the measurement device here know how much current is circulating through the line? Well, it does so by using the CT as its interface to the system. Now, for CT classifications, the most common relaying accuracy class for current transformers is the C class. Now, the C class gives us a maximum limit of ratio error at 20 times rated primary current of 10%, which means that when the current through the primary of the CT is 20 times the nominal current, the CT is required to give you no more than 10% error when nominal burden is connected to the secondary of the CT. What I'm trying to say here is that the higher the current, the higher the allowable error for that CT is going to be. If you look at a CT's excitation curve, we can notice that on the CT excitation curve, the higher the voltage on the secondary of the CT, the higher the excitation current. Now, the error on the CT is the excitation current of that CT, which means that the higher the current on the primary, which in turn is going to become the current on the secondary, the higher the excitation current, and they have a fairly linear relationship up until the point of saturation, where, well, everything goes and becomes very difficult to predict, which means that when we need it the most, then we have the most error. What I'm trying to get at here is that you cannot make a crisp decision. You cannot say that if the impedance that you just calculated is strictly lower than the impedance of the line, then trip, because there are too many errors that go into that calculation that you have to be able to protect yourself against. Otherwise, you will not have a secure protection. So what is done typically is we use a safety factors that, for example, for this relay, if this were a distance relay and it were measuring distance on this line or impedance on this line, and it was using that measurement to make a decision, hey, do I have to trip? Do I not have to trip? You would not want it to trip instantaneously for any fault beyond 80 to 90% of the total distance of the line. Why? Because those 10 to 20% inaccuracies are used to account for all the possible errors that go into the calculation of those impedances. And remember that you don't only have errors in the measurements that you're doing, you also have errors in the assumptions that you are doing about the line, because the line impedances themselves could be erroneous, not by much, but they could be erroneous, and they could change over time. So a 10 to 20% safety factor is good. Then you set a zone 2, which can be used to account for all the 100% of the line and even a piece of the adjacent line. And then that zone 2, you're going to trip it, not instantaneously, but you're going to give it some intentional time delay. Okay? Now, so again, zone 1 should never reach beyond the remote bus. It should use that 10 to 20% as a safety factor. The inaccuracies that we have here are basically the relay measurement accuracies. The relays themselves are not 100% accurate. They are designed with an acceptable error of around 3%. Manufacturers try to make them better, but they're not 100% accurate. Then you have those current and potential transformation errors that we just talked about. And then you have the line impedances, and then you have the transients that happen, etc. Then you have the zone 2, which again, it's not instantaneous, and the time that you use for the tripping of zone 2 should provide enough time for the operation of zone 1 protection, and also for the operation of the breaker on B in the case that B is tripping the lines, because this protection here, the zone 2, will see faults all the way over here, but you have to give time to B to trip in the case the fault that it's seeing is in this area here. So now let's talk about the characteristics that are used on distance protection. The impedance relay, which is apparently what we are talking about, is the, let's say, natural extension of the concepts that we are talking up to this point. Why? Because here you can see that if you put the relay here at the center of the coordinates here, then for impedances in the positive direction here, you will have the line, and you will say, okay, if the impedance is lower than anywhere on this circle, then I trip. But if the impedance is higher than places on this circle, then I don't. The problem with this type of characteristic is that it is not inherently directional. So you have to supervise it. You have to make it directional somehow. Also, it has an uniform reach in all of the plane, which means that you may not want to use it. It is the simplest type of impedance relay that you can come up with, but it has been superseded by characteristics such as this one, the Mo protection relay. We are not, unfortunately, going to have time to devise the characteristic of the Mo relay. You can find that on the literature out there. But the Mo relay is inherently directional, and all the faults or all the behaviors of the system that give you impedances inside this characteristic will be the cause of a trip. Anything outside will not, and you can set Mo's with different zones, like we talked in previous slides. Now, this Mo is also known as admittance relay. It is an admittance circle that passes through the origin, although in some cases you can use an offset, or some operations in the system can cause the Mo characteristic to be modified in one direction or the next. The reach along the resistance axis is less than the impedance relay. Remember, in the impedance relay, we have a uniform reach along the impedance, along the resistance axis, but in here, the reach on the resistance axis is okay. The reach on the resistance axis in here is smaller than, okay, give me a break. Okay, it's smaller than the one that we have on the impedance relay. See that on the impedance relay you have a uniform reach, but in the case of the Mo, we do not have a uniform reach, and then you can modify this by modifying the MTA. Now, one of the problems that we have with the Mo is the fact that if you see this line here, this line gives me the load, and the load can sometimes be so big, and remember, bigger load means lower impedance, can be so big that it can get into the operating characteristic of the Mo relay. For that, you use blinders, which can act as a way of protecting the Mo from tripping for load, but it can also act as a way of limiting the reach for resistance in the case of resistive faults. Now, this screen that we have here is a screen from a software that allows you to configure all of the features of the Mo characteristic for the line to neutral, line to line, or three-phase faults. It can allows you to do the ground compensation, and then it allows you to test those characteristics. There is also the three-zone Mo, as you can see here. In this one, what we have is 3 zones, each of which has a higher reach, and but they are all on the same. They're all on the same angle, because the angle that you see this circle on the Mo circle, the angle that you see that circle, let's say, moved on the plane is what's called the MTA, or the maximum torque angle. That's actually the angle of the line. All right. So another very popular characteristic out there is the quadrilateral. The thing with the quadrilateral is that you're not restricted by the circle form, so you can change this line at will, and you can make it so that, for instance, it doesn't trip for any reactance higher than this value here. You can see this is a straight line, whereas in the mole you cannot do that, because you have a reactance here, and it will trip for any reactances up to this point. But you have no way, unless you supervise it with a reactance line like this, of creating this type of characteristic. Now the quadrilateral is also very popular, but especially now with digital relays, because you can create and recreate at will this type of characteristics. And the good news is that you do not have to be an expert trigonometric wizard to calculate all the different points and whatnot. Both relay manufacturers and test set manufacturers have devised tools that help you by simply configuring or using the configuration points, the extreme points of the characteristic. You can type them here, and then you have the type of characteristic that you want. In this case, we also have a three-zone quadrilateral, and then you have the ability to test all those points along the line. In this case, we are even showing the possibility to do ground compensation on that quadrilateral. And here you can see three types of ground compensation that we did not mention. And I would encourage those who are listening and interested to go and look for the different ways of calculating and how do they affect the testing, because this is one of the things that provokes more headaches to test relay testers out there. Now, polarization. All of these impedance calculations that we have been talking about until now, they're all based on having a voltage to compare with the current in order to determine directionality, which means that when you do not have a voltage that's good enough, then you're going to have trouble determining whether the fault is in the proper direction or not. Now, what polarization means in this case is which voltage do you use to determine the direction of the fault, right? Now, the types of polarization, the most popular types of polarization out there are, the first one is called self-polarization, which uses essentially the same voltage that you have on the faulted face or the faulted loop. That has a problem, which is that usually when you have a fault in a line and the fault is in a particular phase, the voltage of that phase collapses very quickly, which means that sometimes you do not have enough voltage to compare with the angle of the current in order to determine directionality. Cross polarization, on the other hand, uses the voltage of one of the healthy phases as the polarizing quantity. It has to be the phase that is in quadrature with your current. It has the advantage that if it is a healthy phase, the voltage is not going to drop so dramatically. In other cases, they use memory polarization. One of them is memory self-polarization, which what it does is, at the moment of the fault, it goes back one cycle or two or three, depending on the algorithms that you're using, and uses that value of the voltage that resides in the memory as the polarizing quantity. You also have combined polarization, Now, combined polarization, the most popular one is using positive sequence voltage polarization. No matter how bad the voltages are, you can always calculate the sequence networks and then use the positive sequence voltage for polarization. Now, the polarization methods used change the behavior of the protection characteristics. The modes change a little bit. So it's important to know what type of polarization method is used in order to protect the system properly. Another thing that I wanted to talk was what's called the source impedance ratio. Now, the source impedance ratio is defined as the ratio of the source impedance, you can see it here, to the line impedance. In the case of the relay, for the relay, is the ratio of the source impedance to the zone impedance setting. Not the impedance of the line, but only the zone impedance setting. If it is 80%, then the 80% impedance that you have on the line. Now, the SIR or the SIR is a measure of the magnitude of the faulted loop voltage seen by the relay. Why? Because the voltage here, the voltage that you see, the voltage that the relay is measuring, is going to be equal to the voltage at the source minus the current times the impedance of the source. So the higher this impedance, and remember, this current depends on several things, but the current is going to be higher the closer the fault is to this point here. Correct? Because you're going to have less of the impedance of the line in between this point and the fault. So what's going to happen is that the higher the current that circulates, the lower this voltage is going to be. And the higher this impedance for the same current, then the lower this voltage is going to be. Which means that if you have a high source to line impedance ratio, it means that your source voltage is going to collapse very quickly, which is going to give you a lot of headaches when it comes to testing the relay, but it's also going to give you a lot of headaches when it comes to setting the relay properly, because if the impedance, the ratio or the source impedance ratio is too high, sometimes it doesn't make sense to protect the line using a line protection. Now, how is this ZER related? A ZER greater than 4 are classified as short. The lines that have a source impedance ratio of 0.5 to 4 are classified as medium, and lines that have a source impedance ratio of less than 0.5 are classified as long line. Why is that? Why is this like that? Well, first of all, remember that the source impedance ratio is the source divided by the line. The longer the line, the bigger this impedance is going to be, the lower the SIR. The shorter the line, the lower this impedance is going to be, the higher the SIR. Okay? However, it doesn't matter how long or short in terms of meters, in terms of kilometers or miles, the line is. You cannot use the length of the line as the criterion for classification. You have to calculate the SIR using one of the many available methods for calculating the SIR, and then make the decision, because a line that may be short in terms of miles could be long in terms of impedance, and the other way around. Okay? So keep that in mind. So the problem that we were talking about for short lines is that the higher the SIR, the more complex the line protection is going to be with zone 1. Because the higher the SIR, the faster the voltage is going to collapse. So it's going to make it very difficult for the relay to differentiate between faults that are actually in the zone or out of the zone. And then the measurement errors are going to be more pronounced. And then you're going to have higher current and voltage transformer errors, and etc. What I'm trying to say here is that if the line is too short, then maybe you should consider other types of protection instead of using distance zone 1 protection. Now, I wanted to talk at the end about directional comparison schemes. Distance protections are usually used as part of schemes in order to improve the behavior of the system and prevent the nuisance of bad tripping. Essentially, directional comparison schemes, what they do is you have several relays looking into a line, and both relays see the line, they both see the fault somehow, and they talk to each other somehow. So the relay A says, hey, did you see the fault? Yeah, I did it. Okay, let's trip. Essentially, that's the essence, even though, there are many differences between them, and the first one that we're going to see actually doesn't require the permission from the other relay, but essentially what happens in schemes is that you have relays on both ends of the line, and they're both looking at the same line, and they're trying to make a decision by communicating to each other as to what did they see, okay, happening on the line. The most popular directional comparison schemes are the direct under-reaching transfer trip, or DUTT, the POTT, or permissive over-reaching transfer trip, the PUTT, permissive under-reaching transfer trip, and then we have directional comparison blocking and directional comparison unblocking. I will only be talking about the first three. We don't have, I don't think we have more, we have time for more than that. Now, in the case of direct under-reaching transfer trip, well, the name says it all. It's direct trip, which means that as long as one of the relays sees the fault, it trips, and then it commands the other guy to do the same. Under-reaching, because they're only looking for faults on the first zone of protection, okay? And transfer, because, this guy is telling the other to do it. So what happens here is that if, let's say, relay 1 sees a fault in this point here, he will trip immediately, and then it will send the trip to this guy over here, right? And this guy will trip immediately without any other consideration. What happens here is that, let's say we do not have the scheme. If we do not have the scheme and we have a fault here, which is zone 1 for this guy, for CB1, and it's zone 2 for CB2, what's going to happen is that this guy is going to trip instantaneously or with no intentional time delay in maybe under a cycle. But then this guy over here is going to see the fault here as a zone 2. Now, zone 2 is usually tripped around 20 cycles or so. So even though this guy tripped immediately, this guy is going to wait 20 cycles to trip. Now, in the case of the scheme, well, here we have this guy tripping immediately and then sending a trip command to this guy here, which is going to trip the breaker immediately. What's going to happen is that we're going to trip a lot faster with the scheme than we did without it. In the case of the next one, which is the permissive under-reaching transfer trip, well, in this case, it's permissive, which means that there has to be some supervision on both relays in order to allow the trip. It's under-reaching, which means that both relays need to see the fault inside the line, and it's transfer because this guy sees it, and then this guy is gonna say, yeah, I saw it, now you're telling me to trip, let's do it. The same thing happens here. If we, let's say we have a fault over here, which is outside the reach of this guy, but it's within this guy, zone 1. This guy is going to trip immediately. Now, this guy here is not going to see it on the zone 1, but it is going to see it on zone 2, which means that it will allow the trip if this guy sends the command to trip. Now, this guy will send the command or the signal immediately as it sees the fault and trips. So the signal will reach this guy. He will say, okay, I have your permission. Do I see it? Yes. And I trip. Okay. It's going to have a similar effect to the scheme before. The difference is that this guy has to see the fault. Okay, it's not like the other guy where there was no permission. There was nobody was. I wasn't this relay. There had no supervision. It was tripping simply on the direct trip here. This relay was tripping simply because it received the trip command from this relay. In this case, it receives the enable, but it also needs the permission from its own functions. In the case of the overreaching, what happens is different. In this case, both relays need to see the fault with the zone 2. In the case, it's similar to the other one, but in this case, both relays need to see the fault on zone 2. And what happens is this one, let's say the fault occurs here, it will see it with zone 1 and zone 2 because it's very close here. When the fault happens here, this guy will see it with zone 1, but will also see it with zone 2. So this guy will say, hey, I'm going to send you the command, and this guy is going to say, yes, I have permission to trip. If the fault happens outside, this guy will see it with zone 2, but this guy won't see it with zone 2 because zone 2 is only looking ahead. So even though this one sees it with zone 2, it doesn't receive the permission to trip, so it doesn't trip and the line is secure. At the end of the presentation, I wanted to mention that Megger has a line of products that allows you to do all those testings, and it makes the life of the tester a lot easier. You can go ahead, and I invite you to download this software here. It's called RTMS. You can download it from our website, and you can fiddle around, play around with it to help you understand the concepts that we discussed on the webinar. And I also encourage you to look for further information on our line of relay test sets, which can allow you to test single protections or systems, as you can see in this slide here. The references that I used on the presentation are in this slide here. You will receive it. I, in fact, used probably more than 200 different articles and papers and things for this presentation, but I wanted to put together this list in particular because it contains the IEEE and SIGRE documents that, in my opinion, are more important for you guys to consult when trying to understand and study and get into the world of distance protection. So with this, Michael, I'm done.
Okay, thank you so much for the presentation, Abel. That was a good presentation. And guys, now let's move on to the question and answer portion. But before doing so, please be reminded that for those who are leaving, please don't forget to answer the survey that will pop up on your screen. That will really help us in improving our future webinars. So now let's move on to the, if we have time, yes, we have time. Maybe some few questions. Assume, are you there? Sorry.
Yes, I'm here, Michael.
Okay. So the first question is how to make calculation setting for resistive blinder for each zone, face to face and face to ground. Can you answer this one?
Okay. Yeah, actually, this is not basic distance question. But I will try to answer that that I know. So actually, as I know, the resistive blender is very when faults coming because the maybe tree touch the system to the line. So how to make calculation? As I know, every relay manufacturer, they have different way how to calculate it. I know most of case they don't put this calculation on the manual. Most of case we need to talk directly to the relay manufacturer guy or uh, to get this calculation. In example, like in GE relay that I know, to make it a simple calculation to find resistive blender, you just need to calculate by ratio 50 divided by ratio CT and then multiple 2. So this is one example how to calculate based on the certain relay. So I recommend you try to discuss with the relay manufacturer guy to get this calculation. Yeah, Michael.
Okay, yeah, because it has different blinders, so different manufacturers has different approach in doing the characteristic impedance. We have some more, we have some quadrilateral, we have combination, and for the blinders we have so many types. We have type 1, type 2, and type 3 blinders. And yeah, you're correct. Some different manufacturers have different approach in computing these blinders. Okay, so for another questions, how to make cascading several distance protection if some substation have many bay line with different direct load flow, different line length and conductor. So basically, guys, for distance protection, we normally use it in a radial line, meaning, for example, you have a transmission line. That is a radial line in a straight long line. So that is the proper usage of the distance protection. Now, if you have so many bays, then you have feeder protection relays, you have bay controllers, and you can use that for protection of the bays. And also, that's why we have these different transfer trip schemes like the POTT, POTT. So if you have some loops and you have this distance protection, of course, you need to do those schemes, right? To supervise also the direction, you need a directional protection relay to give signal to the distance protection relay. Okay. And another question here. I have a doubt that it's not a question. Here, why polarization method is required to do? If you have attended the directional protection basic webinar, I think last week, right? So the polarization was discussed there. So we need this polarization to see the direction, to see what we are looking for. I mean, what direction of the current that we are looking for. It could be forward, it could be reverse. So this polarization will help us. For example, you do the voltage polarization, then that voltage polarization will give you information or will give to the directional protection element or the distance protection element the correct direction of the fault. Okay, for example, you want to do a scheme like please block the reverse direction. Do not trip on the reverse direction of the current. So that's how it is. Just for example. Another question. Let's suppose relay A at point of exporting power to bus, where relay B is at receiving end, then how can relay B monitor considering the non-directional relays are installed? For this kind of setup, sir, and if you don't want to use the directional relay, I mean, if it's non-directional relay, then we suggest to use the uh, um, line differential protection scheme. when we do the line protection differential scheme, then it will look at the local current and the remote current, and it will look at the ratio. So for example, the point A will look at the local current divided by the remote current, and the relay at B or point B will look at the local of the relay A will be seen as the remote end current, and it will also look at its own ratio of the local and the remote current. So that is the line protection or line differential relay. Okay. So for this scheme, sir, if you have this relay on the source and relay on the load end, then I suggest, and if they have both, for example, they have another source at the remote end, then I suggest we put a line differential protection. Okay. So when to use POTT and PUTT? What is the advantage of each? Can you answer this one, Sum?
Just a moment. Yeah. What with this question?
When to use POTT?
Yeah. I don't have any idea for the when to use the POTT. Really based on the relay coordination on your system, but the different only on the both scheme need the permission, but only different with the underreaching and overreaching indication means which parameter to be reference. Yeah, I think like that. Any other comment from you, Michael?
Yeah. Normally, I can see this POTT and PUTT in the loop system. You know, you have two source and you have two lines, but they are connected to each other. So if they have a loop system, and then they can use this POTT and PUTT, meaning you are giving permission to the other relay to trip. If, for example, POTT, if it is overreach, the relay will tell you, oh, it's not it's overreach. I mean, it's not on my actual reach, but it's overreach. So you better trip it rather than me. That is, for example. Then if you use the PUTT, meaning under reach, so the relay will tell the other relay that it's under my reach. Okay, can you please trip it on your side, something like that.
Yeah.
Another thing. Another question. Let me see if I can see more, because we have a limited time. We already past 9 minutes. Maybe these are the questions, so maybe that can be answered through email. Maybe these are the more advanced. So I guess these questions, guys, we have a lot of questions, but I guess this will take a long period of time to answer. So we will better answer this through email. So yeah, in as much as we want to answer this one, the time limits us to do so. So guys, thank you everyone for attending this webinar, and hope to see you again next time. Please have a good day and stay safe. Thank you everyone. Thank you, Grace. Thank you, baby.
Bye.
Tin nhau với con thôi, hồi quả cái thành nhà